David Smith here with one more flipped classroom math video lesson. 3 tips before we start. First, remember you can adjust the playback speed to make it faster or slower as you like. Second, you can pause the video at any point to catch up on your notes or jot down some questions. Third, you can turn on the captions so you can read my words on the screen. Today's topic, estimating limits. This is the first lesson in our chapter on limits. So we're going to cover a lot of the basic introductory stuff in this lesson, and then we're going to use some tables to estimate limits for certain functions. But we're going to start by taking a look at this rectangle here. I've put a rectangle, width and length, and I've asked this question here. If the perimeter of the rectangle is 24, what is the rectangle's maximum area? And a lot of the math that comes in calculus is about maximizing things, and derivatives help you do that as well. So let's take a look at that. Let's just do sort of a test kind of way to see if we can find out how we might maximize area. You probably already have the solution in your head if you've looked at this, but I want to go step by step because we're going to develop this idea of a limit. So here's my first try, right? If I'm 4 by 8, that does give me a 24 perimeter. 4 times 8 is 32. That gives me an area of 32. Cool, that looks good, but let's try something else. Let's try increasing this one to 5 by 7. That also gives me a perimeter of 24, but now my area is 35. So I'm getting bigger. Now think, what comes next? 6 and 6, right? That gives me the same perimeter. That's got a perimeter of 24, but now my area is 36. And indeed, we are now at our maximum area. If I increase this, I'm going to decrease that, and it's going to end up doing things like these. So the area is going to drop back down. So this is my maximum area of 36. Okay, so let's formalize what we just talked about. So I'm going to do it 2 ways. One in words, just like we talk about a limit, and then we're going to introduce you to the notation of how limits work. So, first off, in words, stated as a limit, this problem stated as a limit would go like this. The limit of area, which we're using A, so limit of A as width approaches 6 is 36. Okay, so that's basically describing what we just did with our rectangle problem. Now we can use notation for this. It's pretty simple. Limit of A as W approaches 6 equals 36. So this is our notation for this problem. Okay, so let's generalize that result. Here's general notation. The limit of f of x as x approaches c is L. That's the limit. We can say it in words. The limit of f of x as x approaches c is L. So there we go. Now we have our basic notation, our basic concept. So now we can start evaluating more complicated situations than this rectangle problem. Okay, so let's do some limits with algebraic functions instead of a geometry problem like the one we just did. So here's one for you. The limit of 3x minus 2, here's our function, as x approaches 2. Now in this case, you could just plug the 2 in and you're going to get 4 for that. But let's use this technique of using our table to show what that is. So what I'm doing is I'm getting closer and closer to 2. I'm plugging these numbers into our function so I can plug x in and I get f of x out. So when I plug in 1.9, I get 3.7. When I plug in 1.99, I get 3.97. Now let's check the other side of 2. Getting really close here, 2.01. If I plug that in, I get 4.03. If I go up to 2.1, I get 4.3. So you can see that as I approach 2 from each side, I'm getting really close to 4. And you can check now by plugging 2 in, and you'll get 4. So the limit for this one is 4. Now, it's not always so easy, okay? So I want you to pause the video and try to do this one. The limit of, as x approaches 0, of x over the square root of x plus 1 minus 1 as x approaches 0. So see what you get with that. Okay. Now, you probably noticed something. If you went to plug 0 in just to do a check, like we could with this one because it worked, you're going to find that you're going to get 0 on the bottom of your fraction. And you can't evaluate that. That's undefined. So we can't figure out what this limit is by plugging 0 in. Because what's going to happen is this is going to be the square root of 1, which is just 1, minus 1 makes the bottom of our fraction 0, and we can't evaluate that. So go ahead and try the table method and see what you get for your limit for this function. All right, so here are my numbers plugged into that table, and my results, I rounded. When you do the math with these values in for x, you're going to get a decimal string that goes on forever. So I rounded to the thousandths or the 10,000ths, and check it out. I'm getting closer and closer to 0 as I go this direction, and notice how I'm getting closer and closer to 2. And on this side, as I approach from the positive side, as I get closer and closer to 0 here, I'm also getting closer and closer to 2. So that's cool. That lets me tell you that the limit of this is 2. Now, we can't check it. We can't plug our 0 into our function and get 2. So this is where the table is super important. Okay, let's take a look at the graph of this function because it's going to bring out an important point. So I've put up my coordinate plane right here, and I've got it all set to go. The smallest number we can use for x is -1. Do you see why? Take a look at the function, see why. If you use a number that's more negative than -1, you're going to get a negative number under the root sign, and right now we don't do imaginary numbers. So my furthest left point here is going to be at -1. Okay? And then the function heads right to 2, because that's our limit. But it can't do 2. So what we do is we're going to graph it something like this, and we're going to put a little circle around that. So that indicates, that shows us that the function right there is undefined. Okay? We can't put in 0 for x. It just does not work. We have an undefined function. It's kind of like math can't handle that, it's broken. So we show it on the graph by putting an open circle there to indicate that that point, which right there is 2, there's no value for our function. It's undefined. Okay? So will this function ever give us 2? No, you can't do it. You can do all of these values in for x, but you can never put a value in for x that will spit out 2 because the function goes undefined. This is kind of like a problem that is sort of in the popular mind is, let's go halfway to the wall. Let's go halfway again. Halfway again. Halfway again. What's the limit? The limit's the wall, right? That's as far as you could possibly get. Are we ever going to get there? Technically, no. We're not going to get there because we're always going half the distance. So this is kind of like that. We're never able to get to our limit with our function. However, we can figure out what that limit is algebraically, and then we can show it graphically. Now that you've watched the video, take a moment to jot down any additional notes, some questions, or a quick summary of the lesson. You can also re-watch the portions of the video that were a little bit challenging for you. If you enjoyed the video, please click like, and if you'd like to help me grow my YouTube channel, please click subscribe.